All right, so like I was saying earlier, last week we spent a couple days on triangle congruence, which basically said two triangles are more or less the exact same triangle. Maybe they're in different places in space, maybe they're overlapping. But we went through a lot of different proofs to determine whether or not two triangles were in fact congruent. Today, we're taking a slight detour. Still going to be focusing on triangles primarily. What we actually covered today could work on other polygons. So four-sided shapes, 5, 6, 7, 8, and so on. But our main lens is still going to be through that of triangles. So instead of focusing so much on are they essentially the exact same triangle, we're going to be looking on, or more specifically, similar triangles. So they still have some things in common, but they're not exactly the same. So in order to be considered a similar polygon or similar triangle or any shape for that matter, they are considered polygons with the same shape, but different size. Same shape, but different size. So polygons are similar more specifically if corresponding angles are congruent. So no changes there. The angles still have to be congruent. That's what gives the shape its shape. But the corresponding sides, since the size of it is changing or varying, the corresponding sides have to be proportional. I'm actually going to highlight that real quick. That's going to be a keyword today, proportional. Quick throwback to Algebra 1. We've solved proportions before. Those are the things that look like two fractions set equal to each other. So despite maybe some of your frustration, fractions are going to be involved today rather heavily because that's going to be determining how proportional they are. Now, the good news is what we want to see, not to spoil too much of the surprises, when we have two fractions, we want to see that they simplify down to the same thing. So really, more or less, it's just simplifying fractions, not necessarily adding or subtracting or multiplying or dividing. It's more or less just simplifying them, but there's no way to avoid them altogether.
Will there be any decimals?
So the next thing I'm actually about to talk about here could be given to you in the form of a decimal, but fraction would be more preferable because when we go to compare corresponding sides, it's going to have a very fractional appearance to it. And I'll show you what I mean here in just a moment. So yes, it could be done in decimals. For some of the things we're going to look at today, I would say fractions are going to be a little bit easier.
What I meant to ask is everything like with this student is just on straight fractions. Not like you won't give me like a decimal, then you got to turn it to a fraction. Like
Oh, converting back and forth between the two. I don't want to lie to you. I mean, nope, all fractions. Yep, no jumping back between the two, back and forth anyways. All right, so the angles are still congruent. The sides are now, instead of being congruent, they are proportional, meaning a certain amount larger or smaller than the other. Now, to determine that size difference, we use a ratio between the corresponding sides, which is referred to as a scale factor. And then there's a little kind of like a side bit of information. This actually will play a role, I think, towards the end of this, beginning of our notes here, end of the beginning. which states that if polygons are similar, which we're going to see how to be able to determine that in just a moment, then so long as you can prove that they are similar, you can actually say without a bit of doubt that their perimeters are also proportional. So if all their sides are proportional, then their perimeter must also be proportional as well. Now, let's talk about that scale factor. Now, something I want to draw your attention to right off the bat, before we even do anything with it, is that very bluntly, it says that the order does matter today. Now, the reason for that, if you think about it, the ratio is just in a way a type of division. And unfortunately, division, similar to subtraction, the order is very important. It's unlike our multiplication and addition, which you just do it any which way that you want, you still get the same result. Order is very important here. So what we're going to take a look at is determining some scale factors between these two triangles given to us in this diagram. And you'll notice, hopefully, as I'll show you here, is that in the diagram, we're shown that each of their angles have a corresponding congruent angle. So A and D are congruent, B and E are congruent, C and F are congruent, thanks to those visual representations. But then very quickly, you'll notice that AB, BC, and AC are not congruent to their corresponding sides. And that's because these are not congruent triangles, they are similar triangles. Now, to figure out what scale factor is determining their similarity, you have to set up a ratio and you use the corresponding parts. So for example here, it did say order mattered. So since it's asking what is the scale factor of ABC to DEF, our scale factor is going to have the first one on top and the second one on the bottom. Now, in order to get that factor, what we're going to do is take a corresponding side length of one triangle and put it over the corresponding side length of the other triangle. Of course, we're going to pull ABC's side on top, DEF's side on the bottom. So I'm just going to kind of work my way around, and I want to show you a neat trick. So I'm going to start with side AB, which is a length of 8, over side DE, which is a length of 12. Now, let's say, for instance, I didn't use that side. Instead, I did BC, which is 10, over EF, which is 15. Or maybe even lastly here, maybe I did AC, which is 14, over DF, which is 21. Now, initially, they all look like drastically different ratios. But do you know what they all simplify to? Eight over 12, you can take out 4, which would bring that to 2/3. 10 over 15, take out a 5, which brings it to 2/3. And a 14 over 21, you take out a 7, which brings them all to the same scale factor of 2/3. So if I were to read it again, the prompt is, what is the scale factor of ABC to DEF? I can now say that triangle ABC is 2/3 the size of triangle DEF, which if you look at it, 2/3 is smaller than a whole amount, right? And ABC is clearly smaller than DEF. And if I were to measure it exactly, it's exactly 2/3 the size. Now, if you were to flip that around the other way, to consider the scale factor in reverse. All that changes is the order in which you write your ratio. So you'd put DEF on top and ABC on the bottom. And all it does for each of your corresponding sides is it just flips all of them as well. So instead of 8/12, you're comparing 12/8. 10/15 becomes 15/10. 14/21 becomes 21/14. But because they're still corresponding, it's not quite the same. The scale factor also flips to be 3/2. Now, again, not asking you to convert it necessarily to a decimal, but 3/2 is an improper fraction. That's technically 1.5, which tells me that triangle DEF is 1.5 times bigger than triangle ABC. Now, the last one's a bit sly. It's asking what is the ratio of the perimeter of DEF to ABC? Well, here's the thing about that. Oops, that's not what I wanted. Neat to know I could do that though. If the triangles are in fact similar, which we proved, the scale factor used for the corresponding sides from DEF to ABC is the same scale factor that you would use for its perimeter. So this would be 3/2 as well. Now, if you wanted to, if you're like, you know what, I'm a bit, leery of that. If you wanted to, you could add up all the sides of one triangle to find its perimeter, add up all the sides of the other triangle to find its perimeter. So long as you put the perimeter of DEF over the perimeter of ABC, you should still, in fact, get that same exact ratio. So fractions are big today. And the order is important. Adding to our vocabulary a little bit further. So again, throwing back to our last couple lessons when we talked about triangle congruence, we had a congruency statement. Similarly, no pun intended, there's a similarity statement for which we're going to use a slightly different notation. It's actually only part of the congruent symbol, which is the little, I think it's called a tilde. And as such, so long as you can prove that two polygons or triangles today are in fact proportional based off of their corresponding angles being congruent and their corresponding sides being proportional, you can write a similarity statement for those two triangles. So again, we proved that they use the same scale factor in the triangles up above. So if we were to write a similarity statement for those two triangles, we would say that triangle ABC is similar to triangle DEF. Now, order is important, just like the congruency statement. Notice A is first in my first triangle, so is D in the second. That's because those are the corresponding angles. B and E are second. That's because they were corresponding. C and F then are the third ones. Order is important, especially if you're going to pull information from that similarity statement. Any questions so far? Haven't gotten to the proofs yet, other than just making some calculations. Before, we didn't have to worry about calculations because both triangles, when we're talking about congruence, both triangles are the same. Here, they're not, well, they are the same shape, but they're not the same size. So a calculation is factored in or considered. So a little bit more math than what we've done in the last couple of lessons, but that's okay. All right. So we're going to take a look at these examples here. We're going to list all the congruent angles, but then also write a proportion that relates all of corresponding sides for each of these. And we're given a valid similarity statement. So even though it may not look like it initially, because this triangle is kind of a rotated, smaller version of the other triangle, we're given the similarity statement, so we don't have to assume anymore. We just have to write the relationships. So remember, order in that statement does matter. So long as someone's not made a mistake here, we could say that angle J is congruent to angle P. Angle K is congruent to angle M. And angle L, my angle and my L look oddly similar, is congruent to angle N. That part, again, shouldn't feel too shocking. It's the same thing we did for congruent triangles. What is different, however, is how we set up our proportion. So again, it's really...
Quick question, Josh. Sorry.
Go ahead.
Can you tell me why you put them in those orders again, just to refresh?
Why I put them in that particular order, or why I paired them the way I did?
Paired them the way you did. That's what I meant.
So let me go back to an earlier example here real quick. So when I wrote my similarity statement here, I was very deliberate to make sure that the order that I put in one matched the corresponding angles I put in the other. So if you notice the notation here, I went A, B, C. So I had to match the congruent angles. A is congruent with D, B is congruent with E, and C is congruent with F. So if I go A, B, C for the first one, I have to match that same kind of pattern, D, E, F, for the second. So if that's how a valid similarity statement is made, if I'm given that similarity statement, I can then assume that that is in fact the case. So the first angle should correspond, those two should correspond, the second angles should correspond, and the last angles should correspond. Does that answer your question? Awesome. All right, so that was how we set up the congruent sets of corresponding angles. Like I was saying before, though, the proportion's a little bit new, but as long as you set up the corresponding sides, you'll still be okay. So I like to kind of systematically work my way through the similarity statement. So I would say that JK is proportional to PM, which should equal the same proportionality from KL in regards to MN, which should also have the same scale factor or proportionality as, I've lost my train of thought, JL, or I'll say LJ, and NP. So again, I just worked my way through the similarity statement. I did JK with PM, KL with MN, LJ with NP. So again, if they are similar, all three of those ratios should equal the same exact thing, which is therefore the scale factor. Okay. Second one's kind of sly, but this is going to be something we'll see here shortly in more detail as we're working on some proofs. But again, we're in luck. We're given the similarity statement, so I would spend less time being distracted by the picture, more time just working my way through that similarity statement, which, assuming it's valid, that tells me then that angle X is congruent to angle R, angle Y is congruent to angle Y. There's that reflexive property. Angle Z is congruent to angle S. And then again, focusing primarily on the similarity statement, I can then set up the proportions that XY corresponds with RY, which should be the same as the relation between YZ and YS, which also should be the same as ZX in relation to SR. Now, if you're a visual person like me and you needed to see some more stuff on the diagram, there's not really anything that we can do for similarity in terms of the sides, but the angles I could say, well, X and R are congruent. Y, well, of course, it's congruent to itself, and S and Z are congruent to each other as well, if you needed to see that. Now, in this case, we aren't doing anything much more with that information. We're just identifying the relationships. Questions so far? Haven't really, doesn't feel like we've done much other than throw out a lot of kind of vocabulary describing things. Well, if not, we're going to slide on down to our next page, which is oriented a little bit more differently here, to say, okay, well, if there's all these ways of proving triangles are similar, there must be a way then, given enough information, to determine whether or not two triangles are in fact similar, assuming you don't have all the information to begin with. So what I'm saying is, back here on the front, I knew almost, other than the exact measurements of the angles, I knew everything I needed to about all the parts of these two triangles. I had all three side lengths of both, and I was told that all the angles had corresponding congruent angles from one to the other. I had lots of information. But as we know from congruence and the proofs that we did last week, we're not always given all the information we need. So sometimes we need to at least have at least the bare minimum to be able to prove whether or not something is in fact similar. So there's only three we're going to cover today. Be careful, there is some similarity. Again, there's that word again, between similarity and congruence. I know we had side congruence, and we had side angle side congruence. There are similarity statements like that as well, but you'll notice that they are all a little bit different because they have that little similarity statement at the end of it. That's to differentiate between the congruence versus similarity. But working through here, we're just going to do one of these at a time. First one we have is angle-angle similarity. So angle-angle similarity states that if two corresponding angles are congruent, then the triangles are in fact similar. Now, the reason for that is technically, if you know two of the angles are congruent, two corresponding pairs of angles are congruent, the third is guaranteed to be congruent just because they have to add up to 180, right? But you don't have to know all three. You just need to know two of them are congruent. So taking a look at the examples here, it's saying determine if the examples below are similar by angle-angle similarity. If yes, we're going to write a similarity statement. So right off the bat here, this one's a bit sly. I see that there's a 75-degree angle.
You add 75 and 74 together,
Okay, so you're looking at triangle ABC, 75 and 74 together.
gives you 149.
149, and we're going to do with that 149.
Subtract it from 180,
And you get,
31 degrees.
so this missing angle right here is 31 degrees, which at that point I can stop. I don't even have to look at the second triangle to find its missing angle, because I see
74.
two congruent sets of angles. Angle E is in fact 74 if you wanted to crunch those numbers as well. But remember, I only need two of the angles to be congruent, because then the third one is assumed to be congruent as well. So here we can say, yes, They are in fact similar. And that similarity statement, again, order is important here. If I said ABC, then it would have to be similar to DEF. Good. Second one. So again, given even less information, I see that angle V and angle Y are congruent based off of the visual aid there. But I need at least a second angle to be congruent, second set of angles to be congruent as well. What's that? So there is a reflective quality in the terms of how the triangles are related, but I'm looking specifically at the angles themselves. Is there something?
Can you use the midpoint or no?
Well, I don't have any visual clues as to there being a midpoint. What's that?
You use the right angle, it's not the hypotenuse.
Well, in order for us to even be talking about hypotenuse, at least one of them would have to have a square. And since it doesn't, I can't, even though it looks really, really close, hey, it's one thing that it comes up all the time. There are vertical angles in here at X. These are vertical, and vertical angles are always congruent. Very sneaky way of squeezing in some congruent angles on you. But correct me if I'm wrong, that's two sets of congruent angles, which means that yes, these are in fact similar based off of angle-angle similarity, which I need to be careful here. If I go WXV, I have to match it. So W is the one that's not marked. So ZXY. Good. So as long as either if it's already given to you or you can somehow defend that it's true, in this case, all vertical angles are congruent. All you need are two sets of congruent angles to determine similarity. Second form of similarity is side, 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 which simply states that if all corresponding sides are, there's that word again, not congruent today, but proportional, then the triangles are similar. So I'm going to determine based off of side, side, side similarity, whether or not these triangles are in fact similar. Now, again, I can kind of get a sense as to what orientation they are with respect to each other and which ones should potentially be corresponding. So if I were to look at this here, if I did QP, I'm going to color code mine here, QP and TS, I have 3/6. And then if I did QR and TU, I'd have 5/10. And then PR and SU, which is 4/8. What do those all simplify to?
1/2.
1/2. So they're all proportional because they all share the exact same relationship, same ratio of 1/2. So QRP or QPR, or however you want to name it, is half the size of TSU. But I'm not worried about that right now. I'm just more interested in the fact that they are in fact similar. So I could say yes. Based off of side, side, side similarity, I can then state that triangle QPR is similar to triangle TSU U. So again, that one involved a little bit more math. We had to kind of check those proportions there. But they all have a ratio or a scale factor of 1/2 going from QPR to TSU. D, same thing here. Again, they look about the same orientation. So if I was to go through here and color code again, I would say the 30 probably would go with the 24.
Five and 28,
35 and the 28.
32 and 25.
So 35, 28, 32, and 25. Except, let me think there, 30 over 24 simplifies to, if I take a 6 out, 5 over 4. 35 over 28, I could take a 7 out, which would be 5 over 4. Well, that's looking good. 32 over 25. Shoot, 25 only has factors of 1, 5, and 25.
Yeah.
Guess what? That one side, even though the first two were proportional, all 3 sets of sides have to be proportional. And that last one, even though visually they look like they could be similar, that last one's enough to say, nope, not good enough. So no, they are not similar. So this would be another example of looks alone aren't enough to make a definitive statement. Last form of similarity that we can use for proving is side angle side similarity, which says that if 2 corresponding sides are proportional and the included angles are congruent, then the triangles are similar. So I know we've seen it before, but the angle in question has to be the included angles. So the angle that's between the 2 sides that we're checking for proportionality. So if I take a look at the next example here, determining based off of side angle side, well, very clearly it's kind of nudging me in the direction I probably need to go. I have 2 sets of sides and the angle included between them. That seems to be where it's wanting me to focus. So if I were to kind of color code these again, I would say KJ and NM probably are supposed to be proportional. So 8 over 6. And then that must mean KL and NP are meant to be proportional, which 20 over 15. Now correct me if I'm wrong. 8 over 6, I can take a 2 out, would give me 4 over 3. 20 and 15, I could take a 5 out, which would give me 4 over 3. So we have enough to say that those 2 corresponding sides are proportional. And then how do I know the included angle is congruent? What's that?
It's there though.
It's there though. Yeah, that's actually as easy an answer as that. That little arc in there is telling me that angle K is congruent to angle N. So we can say, yes, they are in fact similar. And that similarity statement would then be, oh, I don't know, JKL is similar to triangle MNP. And the last one on this page, again, still thinking in the frame of mind is side angle side similarity. I I'll give you the one that's so obvious that it's almost hard to see. Angle A is congruent to angle A. They both share that same angle.
So if that triangle is in the B corner,
If you'd slid it up to B and said B and D were the same, then you would say that they were congruent, yeah. But since they both share a vertice of A, that angle is shared between them. Now, then the proportional sides, hopefully then are on either side of that angle. So if I'm looking at this here, this one's kind of sly because it's one on top of the other. So I would be doing the 15 regards to 25 and the 12 with regards to 21. Make sure the order is consistent. I'm going to do the small one over the large one. So 15 over 25 and 12 over 21. I think 15 over 25, if I take a 5 out of each, gives me 3 over 5. 12 over 21, I can take a 3 out of each, which gives me 4 over 7. Are those proportional?
No.
They are not, which then means even though they have a congruent angle, there's not enough information here. Well, actually, there's enough information here to say that they aren't similar because their corresponding sides are not proportional. All right. So zoom out here a little bit. So we have 3 means of determining triangle similarity. So we're actually going to use those to do some informal proofs. We're not going to do the little proof table method where we make a statement, give a reason. We'll save those for congruence, just because they're much more cut and dry. Instead, we're going to use that information. We're going to have some diagrams, and we're going to try to pick out enough information to say whether or not they are similar. And if they are, we'll write the similarity statement. So we have to be careful because some of these are sneaky. They give us just enough information, but we have to look at it. First one being no exception. So nothing's labeled other than the vertices and these symbols right here. What do they mean? Parallel set of lines. That's interesting. Because then technically this side, or well, this line right here, our segment, is a transversal. And then separately, this segment here is also considered a transversal. Now I seem to recall transversals did lots of things. For example, angle C and G are alternate interior angles. So I'll make a note of that. Angle C, I said C and wrote G. Angle C is congruent to angle G because they are alternate interior angles. But then hopefully I also notice, there's actually a couple ways I could do this. I would say that E equals E because they are vertical. Now I need to be a bit more specific because I don't want to just say E is E. They're not technically the same angle, even though they are congruent. I would say angle CED, which is the one on the left, is congruent to angle GEF, which is the one on the right, and that's thanks to them being vertical angles. Do I have enough information to say that these triangles are similar?
Yes.
By which type of similarity?
Vertical.
Angle, angle. In fact, spoiler alert, this whole section is going to be angle, angle. So we can say yes. I'm going to say by angle, angle similarity, we can then say that triangle CED is similar to triangle GEF. Again, some of these are going to require very little writing. Stop me if I say something, or if I say something and don't write something. If you need some clarification, please let me know. Number 2, there's those parallel symbols again. That's going to be important here as well, because I have new transversals ML and NL, which if I dig a little closer, tells me that this angle right here at M should be congruent at angle PQL, because they are, test your vocabulary, corresponding, same side of the transversal, opening in the same direction. But then the same can be true for angle N and angle QPL. Or if you wanted to be even sneakier, isn't angle L congruent to angle L? It's up to you which pair you need. You only need 2, but we can prove all 3.
Question, but
Why would L equal L? Because it's the same angle. In the so it's angle L is in the little triangle, but it's also the same angle in the big triangle. Yeah, it's a sneaky one, the way they overlap it like that. So I would say angle M is congruent to angle PQL because they're corresponding. And then your choice, you can do N and QPL. I'm going to take the easy way out and say angle L is congruent to angle L, and that's thanks to that reflexive property. Regardless, we proved all 3 angles are congruent. We just needed 2 to say that yes, by angle-angle similarity, we can say that triangle, here's where I need to be careful. I'm going to go QPL is similar to triangle MNL.
I feel like I'm gonna hear the word angle in my dreams now.
Yeah, we're saying angle a lot. All right, number 3. How are we doing on time? I'm going to do this one a little bit faster. If you were to figure out the total equaling 180 and find those missing angles, you would find out that angle S in the larger triangle is in fact 51 degrees, since these are both right triangles, which means conversely then that angle H is 39 degrees. Again, we only need 2 sets of congruent angles. We now have all 3. So we can say yes, triangle, make sure I get this right here, SEY is similar to triangle WHC. Keeping the ball rolling here. Again, if you were to do the math, crunch the numbers here, find those missing angles, it's very tempting right now because angle A and angle F are congruent. But when you crunch the numbers, angle B turns out to be 58 degrees. Angle E turns out to be 49 degrees. And unfortunately, do I have a second set of congruent angles? No. So 1 is not enough. The absolute minimum is 2. Number 5, same idea. If you were to crunch some of those numbers, find the missing angles in each of these triangles, you'll find that in this smaller triangle here next to B, you would get a 22-degree angle. And angle M is 88 degrees, which unfortunately, aside from angle N being the one that they share, they don't have a second set of congruent angles. So this one, unfortunately, is going to be a no as well. And then the last one here, we're already given one set of congruent angles, but there's our old friend again there in the middle, set of vertical angles. I won't forget those today because they've snuck in on us a couple times now. But again, there's two congruent sets of angles, so there's enough to say, yes, they are in fact similar. So I could say that triangle, speed this over a little bit, triangle PXQ is similar to triangle ZXY. So those 6 all used in one way or another angle-angle similarity. We needed at least 2 congruent sets of angles in order to determine whether or not 2 triangles are in fact similar. Moving on to the next one. Now we're going off of side-side-side similarity. Now, I guess I lied partially, Ali, because there is one little decimal that snuck in there without me realizing. But technically, that decimal itself is going in a fraction.
Yeah, and I know how to, I know what that's.
Yeah, that's a recognizable decimal.
Yeah.
But what we're doing here is we need to see that all sets of sides, all 3 sets of sides are in fact proportional. So if I was working my way around here, I would probably say the 9, if it looks like one's rotated from the other. So I would say the 9 and the 14 probably go together. The 13.5 and the 21 should go together. And then that leaves the 27 and the 42. Now, I know that 27 and 42, if I divide a 3 out of each of those, I get a 9 over 14 as well. The one that's sneaky is this one here in the middle. There's a cool way you can check this though real quick, is to grab a calculator, take 9 divided by 14, you get a really ugly decimal, like 0.642857143. But you take that calculator and do 13.5 and divide it by 21, you get the exact same decimal, which means they are in fact proportional, which means that yes, all 3 sets of sides are proportional, so we can write our congruency statement. So I would say triangle KNR is similar to DES. Oh, thank you.
So about the erase a lot more.
Actually, now making a P look like an R doesn't all look right. There we go. So KNR is similar to triangle DES. Again, if you're still thrown off by this little relationship right here, 9 divided by 14 equals exactly the same thing as 13.5 divided by 21. So if you go back and check those later, or if you're watching the video, quick reminder there. Number 8, this one's kind of sneaky because, again, these darn triangles are overlapping. So what we kind of have to do here is I need to know this whole side for that triangle, which is just the 15 plus the 6, right? Just 21. And then I need to know this long side here, which is 28. So basically what that means is don't be distracted by these little parts here, because those little parts there by themselves mean nothing. They are only parts of the sides of the big triangle, not the whole thing. That one was kind of mean. But if I were to set up the corresponding sets of sides here, again, I like to do the smaller one on top. I think I'm just a creature of habit that way. I would do the 15 regards to 21. Work my way around here, the 40 with the 56, and then the 20 with the 28. And I believe those all simplify to 3 out, 5/7. Is that right? So take a 3 out of 15 and 21, you get 5/7. Take an 8 out of 40 and 56, you get 5/7. Take a 4 out of 20 and 28, you get 5/7. So all 3 sets of sides are in fact proportional. So we can say, yes, they are in fact similar. For that, we would then make the statement that triangle, this one's kind of hard to see. The little one is WVX is similar to triangle WUY. Again, you are totally welcome to draw on diagrams as I do. If the information starts off a little bit deceiving, sketch in some extra information or clean it up or put little congruent signs and stuff in there. Do what you need to make the diagram work for you. Okay. 4 more here with side, side, side. It's going to feel like more of the same. Again, this one right off the bat seems pretty legit. Looks like it's a rotated version of the other one. So if I was to go through and pair these up, I'm going to go left to right on this one. Looks like the 5 and the 3 are meant to be paired together, which if I imagine this rotated, would put the 16 with the 10. What's that leave me with? 12 and 7. I don't think any of those simplify to be the others. I don't think any of these are the same, which means, again, if you were to just glance at that, they look almost the same shape. Obviously, the size is different. That's similarity. But when you check those proportions, no, they're not similar. Number 10, oh, there's another gosh darn decimal snuck in there on us. It's okay though, do the little division trick. It should work if they are in fact proportional. This one's kind of sneaky though, because it's a reflected image. So if I were to pair these up here, I would say the 5 goes with the 18. So the 12 should go with the 43.2. And then the 15 with the 54. Now, if you were to sit there and crunch those numbers, 5 divided by 18 is 0.27, and the 7 repeats. 12 divided by 43.2, 0.27 with the 7 repeating. 15 divided by 54, same exact thing. So even though the fractions themselves don't look friendly, they do all in fact equal the same thing. So we say yes. We would say this one's careful, this one's a little backwards. Triangle PAR is similar to triangle YTR.
Another decimal.
Another decimal, man. Oh, and what in the world? I don't know what's happening right here. Those are supposed to be together. So it's supposed to be 14.4. I don't know how that happened. I'm gonna fix it real quick visually on mine. Hide that. And then I'm gonna put the 14 there. Whew. Going through the same process though, again, it looks like a rotated version. I would say then that the 8 must be corresponding with the 14.4. Which means the 17 is corresponding with the 30.6. And then the 15 corresponding with the 27. So again, I would grab a calculator. I would do each of those little divisions. 18 divided by 14.4, it looks like 0.5 repeating. 17 divided by 30.6, also 0.5 repeating. 15 divided by 27, also 0.5 repeating. So again, even though they don't look friendly initially, they're all equal. So based off of side similarity, we can say that triangle ZYX is similar to triangle RWV.
So why did you pick Z first? I think I'm getting stuck.
Great
I see
question.
like when you reflect it when you do the other side, but it's just like, what if I was to put Y first? Does it matter as long as I put it in the same order?
Well, tell me, what order would you have gone in with the first triangle?
I think I would have did X, Y, Z.
X, Y, Z. So if you went X, Y, Z, your second one would have had to been VWR, and that would have been just as good as my statement. Yep, so there's no reason why I started with Z on that one. No mathematical reason, just personal preference. In fact, the first triangle you write down can be in literally any order that you want. There's only so many that you can do, but you pick the order. The second one, however, then is going to be locked in based off of your first decision because your corresponding parts still have to match up. It's a good question. No reason why I chose Z. I just did.
Thank you.
No problem. Last one here, again, another kind of sneaky one because we've got the little triangle in there and then they're trying to throw us off with this long side. They broke it into parts again. That one's what, 20? Oh no. Technical difficulties. So, sorry for that little hiccup there. As I was saying, this side here, be careful. We need to know that whole length in order to set up our proportions. But as I go through there, it looks like the 8 is going to be paired with the 20, the 9 with the 24, and the 6 with the 16. Well, 8 over 20, take out a 4, you take 2 over 5. 9 over 24, you take out a 3, you get 3 over 8. Well, that's already not looking good. And a 6 and 16, take out a 2, you get a 3 over 8. So the last two work, but all three have to work. So this one's a big no. Last section here, again, we'll go a little bit faster because I know notes took much longer than what they have been here lately. But there's just so many varieties we have to cover. Last section here is all thanks to that side angle side. Quick reminder that angle must be included between the two sets of corresponding sides. Otherwise, congruent or not, it's just not enough information. Taking a look at number 13 here. Well, right off the bat, I see our good old friends vertical angles sitting in there at E. And they happen to be included between the two corresponding sets of sides. This one's a bit hard to see because it's kind of a rotated version of the other, where we would pair 6 with the 24 and the 12 with the 48. But I believe those both simplified down to 1/4. So those check out. And then we can say that angle FEG is congruent to angle RES. And that's thanks to them being vertical. But it doesn't matter about the rest of it because we now have two proportional sets of sides with the included angle being congruent. So we have enough to say, yes, they are similar thanks to side angle side. So we could say triangle SER is similar to triangle GEF. Number 14, similar situation here. We have two sets of sides here. We have another vertical angle. Uh-oh. Unfortunately, the included angle would be angle J and angle Y. And do I have enough information right now to say that those are congruent as well? No. Now, if PY and JS were marked as parallel, then absolutely, they'd be alternate interior. But they're not parallel, or at least we haven't been told that they are. So I'm stuck, dead in the water. Fortunately, based off of the information I have, I'm going to have to say no. We don't have an included angle. That's kind of misleading. All right. Last 4 here. I'm going to see if we can do these lightning round. So on this one, kind of sneaky here. They slid in a set of parallel lines, which means that angle M and the right-hand side of angle P are corresponding, which means they are congruent. And it just so happens that they are included between the set of sides that we're considering. 54 over 33 and 36 over 22, which you're welcome to check the math, but I will save you the time. Those are in fact equal. They both come down to something over 11. So we can say yes, triangle CMP is similar to triangle RPQ. 16, again, we're given the included angles already identified as congruent. Assuming that it's a rotation, looks like the 45 would be paired with the 31.5. And that's hopefully equal to the 50 paired with the 35. Double check for me, but I'm pretty sure that those are also equal. If you want to do a quick divide. And if they are, in fact, we can then say that triangle EGF is similar to triangle JHK. Next one, kind of sly. W is equal to W. For this one, though, we would like to know these long sides as well. So don't let those deceive you. So the long side here on the top would be what, 45? This other long side over here, 28 and 14, 42. So we have the included angle is congruent. If you're to check 15 over 45, excuse me. Yes, 15 over 45 should equal 14 over 42. 15 over 45 is 1/3. So it's 14 over 42. So those check out. So we could say yes. Triangle WQR is similar to triangle WSZ.
So did you pick 15 because it was hooked to the smaller triangle?
Yeah, so I did the smaller ones over the bigger one.
Okay, okay.
Yep. If I did it in reverse, I'd have 3 over 1, but the goal is not to, the direction doesn't matter. The goal is that you're consistent. Does that make sense? Okay. So if you start with the smaller one on top and the bigger one on the bottom for the first one, be consistent all the way through. Otherwise, you're going to just have the same ones flipped, which would not be equal, which would throw off your answer. It's a good question there. Last one. Again, we got the included angle down here at L. Of course, it equals itself. It's being shared. Again, it's making us do a little bit of extra work to find these extra long sides here. What's that, 34? So for this one, again, I usually go with the smaller ones on top. The 30 would be paired with the 39. And the 27 would be paired with the 34. double check my math on that. I don't believe those actually work out. So even though you have that congruent included angle, the sides are not proportional, which means they are not similar. Speed round done. Thankfully, the assignment is only one sheet of paper as usual, so not as jam-packed.